Okay, welcome to this talk about, it's actually pretty similar to the lightning talk just before, but that was specific about threading, and this is a little bit more general. So what might be possible at sometime in the future to actually write your embedded system, your small embedded system in standard C++. And this is unfortunately mainly a talk about some dreams. Because, well, it actually started out about 2 years ago when I had some spare time between projects, and at that time I thought, well, it might be interesting to implement ASIO on top of FreeRTOS and LWIP. And at that time, it actually looked like the ASIO networking library and executors might be in C++20. And that was actually still true about half a year ago. But then in San Diego last November, networking was essentially decided not to go into C++20. And just 3 weeks ago in Kona, it was decided that executors will also not be in C++20. So, but yeah, most of what I talk about is really a future, still some way away. However, for the networking library, I think it's pretty stable and everybody knows how it will look like. For the executors library, that is unfortunately not true. But that's a different story, and I will come back to that later. So, so the idea is to have what might be in the standard at some time as a standard API to program against. However, of course, it's only the API. It's not the implementation. So, to actually use it in a small system, you need to implement that API, for example, on top of FreeRTOS or on top of any other thing you might want to take. And unfortunately, when I started at that time, that's my microphone. So I started with, well, I intended to start with porting ASIO to FreeRTOS, but unfortunately I had a hardware which actually had an Ethernet port, but that Ethernet port didn't work because, well, the drivers that came from SDM were just too buggy. So it took too much time to get that one working, and after I actually got it working, the next project came around, so I never actually implemented any of ASIO so far. So what I tell you here is essentially ideas. There's no implementation you can look at GitHub or somewhere else. However, what I want to give you is some references to papers that actually already describe some APIs that might come. So, okay, so this is what the talk is about, but why bother? So, what's the idea about that? And, well, of course, portability, especially embedded systems, is actually an issue. However, my main intent is actually to run exactly the same software on the host as on the target. And then, of course, it's easier to maintain things if you have a standard API and not everybody joining the team has to learn a new operating system or whatever. So for portability, first you have one fixed API to program your application against it. That doesn't mean that porting some application from one device to another, from one RTOS to another is a simple thing. However, it's at least easier. But what you have to do is when you change your RTOS, of course you have to port your implementation that is underneath your API. And however, and then of course you have to test it again, and you'll have to learn all the bugs that your new RTOS has. So typically when you use an operating system, after some time you know where the bugs are, where the strange corners are, and so you have your workarounds, and for a new operating system, of course, you have to learn that again. And if you have software that needs some form of certification, you have to recertify if you change your RTOS. But still, porting is easier if you have one common API. Even if it might be that you have to change some parts in your application, you still at least have the same concepts to program again. Maybe some function calls might change a little bit, and I will come back to that later, why that still will be, even if you have a standard API. And but the abstractions are the same, so the basic structure of your program will still be the same. And you can typically reuse your existing test cases, because on the host you typically don't have to change anything. And yeah, as I said before, my main reason is really I want to run my software as is on the host. And well, of course, on the development host to do some debugging there and some easy tests, but mainly on my build server or test server, so that all my tests can run on the host. Of course, I still need to run some tests on the target, because sometimes are simply different, timing, for example. But I want to run all my unit tests on the host. But even software integration tests should be able to run on the host. And well, hopefully maybe some more. So for example, in the current project I'm working on, we have a test case that actually takes 16 physical devices, and each of them costs about 20,000 euro. So you definitely don't have that around all the time. Sometimes you have to put it in place and take a room full of equipment and do your tests. But normally you are pretty happy if you can do that on the host without any real hardware. And the other lightning talk before Piotr's was about sanitizers, and that is exactly the same thing. On the target, it will be pretty hard to run with sanitizers, but on the host, you want to run most of your application as much as possible using those sanitizers. And well, as we have heard in the talk about unit tests, you need to do some mocking, some simulation, and but it's much easier if you have a standard interface to write your mocks against. And then you can still decide how much of reality you want to simulate. So timing is always an interesting thing, and to introduce errors, of course, is a very interesting thing for testing as well. And my current project is not only with expensive devices, it's also with radio. And with radio, you have a lot of very interesting things that can happen. And if you can simulate that on your host, that will help to detect a lot of problems. And if you have a standard API, your mocks and your error injected devices are implemented against a standard interface, you can reuse those mocks over a lot of different projects. And finally, maintenance. Well, a lot of embedded systems live for a pretty long time, and at some time it might be hard to find developers that still know that old operating system that you use. But if your application is written against standard C++, well, that is something that should still be known. So, okay, now we know why we might want to do that. So what does that actually mean? So, as I said, I want to do it on the host and I want to do it on the target. So what does it mean on the host? As I said before, it's not in a standard yet. It will not be in C++20. So what to do on the host? Well, the good thing is for nearly every proposal we have for C++, we have at least one implementation available that you might be able to use, and as long as and most of that is libraries, so it shouldn't be too hard to put that into your tool chain, and most of that is typically platform independent, so the library often works with Visual Studio, it works with GCC and with Clang. Of course, you always need to do some integration, and that might be a little bit harder if that library implementation actually requires some language features that are not part of C++ proper yet. So, for example, the latest demo implementation for the executors uses coroutines and concepts. Clang supports coroutines, GCC supports concepts, but if you want to have both together, it's pretty hard. So you need a very special build that is pretty brittle of Clang where you can do that. So sometimes it's not that easy, but in most cases things are on the host not too hard. And the real good thing is what you do on your development host is typically not really relevant for certification, so you can just grab what you find. You find some library on GitHub and it works, fine, use it. On the target, it's a different thing. So on the target, you probably have to do it yourself, at least at the moment. And of course, you base it on your existing operating system that you use. Maybe sometimes it's worth to go below the operating system interface. So sometimes it's actually useful to go into the implementation of that operating system and fiddle with that a bit because Piotr said before that it's not really easy to implement a condition variable because of pretty difficult synchronization things. And if you actually can go down to a scheduler, things might become much easier. So you don't really need to implement it on top of your RTOS. Sometimes you can use some lower levels. But that really depends on your RTOS and what are you willing to do. And if you have mechanisms in your operating system that match the standard interface, then generally you can do zero overhead. Of course, if you have a mechanism that is not provided by the operating system, that definitely needs some overhead, but you have to pay that everywhere if you use such features. Of course, the operating system might provide other mechanisms that you could use, but that are not really a concept that will be standardized, so you simply shouldn't use that. And of course, that will probably change in the future, so at some time I probably will have time to actually do my ASIO implementation for FreeRTOS, and other things will come up as well. So that was a lot of theory, so let's look at some real examples. And the easiest one is actually no operating system at all. So in my current project, we have actually two different cores and computing units, and one of them is simply a main loop. And so it can still benefit from standard interfaces, because some things are possible even with a main loop. And then FreeRTOS, just as an example, well, it's first pretty well known, and second, it provides the typical mechanism that all of the small real-time operating systems provide. And then another example, Mbed, as something that actually provides quite a lot more. So the main loop, one of the things you have there is the I/O. You could actually model a lot of your external devices as streams, as standard streams. And that is typically streams for input-output are known, well, at least believed to have pretty bad performance, but that is due to the formatting. So if you actually use the binary stream interface, what you typically will do on embedded system, you will have essentially no overheads, and it's just a question how you implement your stream buffer. But there you can decide whatever you want, but the overhead typically will be maybe zero, maybe even negative. And the other thing is interrupt handlers. So even if you have a main loop, you often still have interrupt handlers. And one thing is that you have to mark them as interrupt handlers, because there's a different ABI for interrupt handlers. And you can do that now with the standard syntax using the double square brackets. So for example, GNU has the attribute GNU interrupt. Whether it's actually a good idea to use that is a different question, because on the host that might have some meaning as well. So you might be careful with that. But what's much more interesting is, well, you have your interrupt service routine, and you need to get your data out of the interrupt service routine to your main loop or to your non-interrupt service code. And as interrupts are asynchronous and can interrupt at any time, you need to use some special tricks for that. And so you could use a standard queue interface for that. Of course, on the interrupt side, that needs to be log-free. However, because on the interrupt side, it's typically single-ended, it's not really hard to have a queue, a concurrent queue that is log-free on a single-ended side. If you have multiple consumers of the queue, for example, it's hard to write a log-free implementation on that side. But on that end, where you have only one agent that feeds it or drains it, making that log-free is actually pretty simple. Simulate your interrupt service routines. I wouldn't do it as the guy Pavel said in the unit test, just as a function call. It's essentially just a separate thread. And that can run at any time, and you can decide when it does something. And the interesting thing is the standard C++ memory model was deliberately defined in a way that it covers interrupt service routines. In the standard, we don't talk about interrupt service routines. It's actually called signal handlers, but it's exactly the same. So everything that is in the standard talking about signal handlers is valid for interrupt service routines as well. So for example, if you use atomics in interrupt service routines, that's fine. And another thing that you typically have in nearly all of your systems is a timer. Well, when we are in a main loop, that is not an event-based timer, but just some timeout, and you want to look at that, has the timeout expired or not? Well, for that you can use Chrono. You just have to define your own clock, which is based typically on your hardware tick, and that's pretty easy. Essentially, you have to implement one function, which is now, and then some ratio things to map that to seconds and milliseconds and things like that, but that's it. So defining that is actually pretty easy. So those are things that you can actually use for main loop. But if you actually have a real operating system underneath, you typically have you typically have tasks that are scheduled. You have queues, you have semaphores and mutexes. And you have some more that is not on this slide right now, which is event-based things. And I will come back to that later. So for example, event-based timer, you typically have that as well, but it's not here. But I will come back to that. So this is a function that we have seen just half an hour before, the xtask create. And what you give it is the function that is actually run in that task. You give it a name that is really only for debugging, and you can also use it for lookup to get a handle to that task. And what's more interesting and what cannot be modeled by a standard thread is the stack size and the priority. And then you have parameters, and because it's a C interface, it's a void star. Well, of course, in C++, you would probably give lambda here, so you don't need any parameters. And then you can you get back a handle to that task that you can use elsewhere. So how do we model that? And well, of course, the first idea is to model that using a std thread. Unfortunately, that is a very specific implementation. It's not a generic interface, and it cannot handle, for example, the priority or the name or the stack size. And also, threads are not a very good generic interface for threads of execution. Actually, this quote is out of the documentation of FreeRTOS, and FreeRTOS is just, as Piotr said, a scheduler, and it allows application to be organized as collections of independent threads of execution. So, to model a thread of execution, well, you have a lot of threads of execution, and most of the people in the C++ committee are not so much interested in embedded systems, but for example on GPUs, where you also have threads of execution, and the thread doesn't really map very well to that. So there is an ongoing work on executors, and it's a very, very old story now. So it actually started in 2007 with the so-called Kona compromise, where it was explicitly decided, okay, thread pools will not be part of C++ OX at that time, which became C++ 11. So, but immediately after C++ 11 was out of the door, we had proposals for executors. So the first meeting was in, I think, in February 2012, and still we don't have them in standard. And the reason for that is executors turn out to be extremely important for a lot of things. And all those things have different requirements on what an executor should be and what interface it should expose. And that's the reason why we still don't have it. Half a year ago, I was actually pretty confident that now we have a stable proposal, and it might actually go into C++ 20, so I actually myself was against that. But then at the San Diego meeting, Facebook came and said, well, all that is, well, actually they came to the Rapperswil meeting in July last year, and already said there, well, we have a different approach and we should go that way. And then there were some teleconferences, and at San Diego it was actually decided, okay, we will rework executors again. And right now I have no idea how the interface of executors will look like. However, I will show the interface as it was half a year ago, because I'm pretty sure the basic mechanisms will still be there, however the actual function calls look like at that time. So the point is you should use executors to model your tasks and not the thread. However, I think it was a good idea that Piotr started with the thread, because that is what you have now. There are no executors now. So the executor model, that actually is a two-part thing. So the real thing is the so-called execution context. And you can have more than one execution context. Of course, the operating system is in execution context because it can handle the different threads of execution, but you can have your own thread pool, which again has essentially its own scheduler. You can even, and that is what I did about half a year ago, you can even model cooperatively scheduled tasks. as executors. And you can have a number of them next to each other, each on an operating system sketch, for example. So this is the execution context. Each execution context essentially has one scheduler. So everything that is in one execution context is handled by the scheduler of that execution context. But in your whole system, you could have several of them. And even in an embedded system, it actually makes sense to have some tasks scheduled cooperatively and others with high priority or whatever that are scheduled by the operating system. And then the actual executor, that is a lightweight handle to the execution context, but the executor actually gives you the tasks. So the executor creates tasks. However, the point is they are handles that can carry additional information. And that is the interesting thing, because what information that holds can be defined by everybody. So it can be user-defined, it can be defined by your implementation. So that is actually the place, for example, to put stack size in, or priorities, or the name. So all the things that FreeRTOS has, that is not really part of the execution context. That can be done in the executor. And so just to show you, this was a proposal in February 2017, so it's actually pretty old. So an executor had essentially, I think, 16 functions to create a task. And then SG1, which is a study group for concurrency and parallelism, said, well, no, we don't like that. So they came actually back with a better one. So the next version, which came in March 2008, well, actually I think that was already one meeting earlier. So they came back and said, oh, okay, we have put it down to 6 different execution functions. So the first one is a fire and forget. So this creates a task, you don't even get a handle back. Which actually is pretty useful in a lot of embedded systems, because you set up your tasks at startup time, and then they run forever. So there is and then typically you don't need a handle to that. So actually, FreeRTOS allows you to give their null pointer, so you don't get a handle back, and often you don't need that. So this would be the function to use there. But sometimes it's actually useful to get a handle back, for example, to join that. So if you actually want to join your task, then you need a handle, so that is a two-way execute. There you get a handle back. And then there's another one that is, it could be useful in embedded systems, so I'm not much a fan of it, which is then execute, which means, okay, when here you get a future which came from another task. So if the first task is finished, now start that second task. And you can chain your things, and the question is, how expensive is it to create a new task? And here we come back to the point that executor context can be anything. And it can be extremely cheap to create a new task because you just have a thread pool with a fixed number of worker threads, and so you get a state function or a lambda that you can convert to a state function and just put that into a queue, and that is your task. So creating a task can be extremely cheap. And then the GPU people said, well, it's actually much easier if you already know you need 100 tasks to tell us upfront and not create 100 single tasks, but just tell us, okay, I want 100 tasks. So you actually have the bulk versions of those three functions as well. So that is the idea of the executor interface, and in one way or the other we will have that in the future as well. It will just probably have different names. We nearly settled to put at least this one into C++20, but that was pulled off in Kona. So we don't even get that one. So I will spare you this one. And as I said before, the executor is a handle to the execution context, and the executor can have additional information. And that additional information is actually modeled by so-called properties. And these properties, well, there are some standard properties. They, for example, define what interface is available. So if you write your own execution context and your own executor, it might actually be quite some work to implement, for example, the bulk versions. So you could say you don't implement them, and then you ask for the property, and it says, okay, it doesn't have it, and then you can say, okay, now I want the adapter that just runs the for loop, so I can still have the bulk interface if I really want it. So we have properties for this one. We have properties whether it has only the single or also the bulk ones, or only the bulk ones might also be an option. Then about blocking, so for example, if you have a thread pool with a single thread, and the point is, if you have an inline executor, which might be an option, so it, whenever you start a task, it just runs that function. That is called blocking because it doesn't return before that function was finished. So this might be an option as well. And stat async, for example, would be actually such a thing that might be blocking or might not. And there are some others, and for example, there's also an allocator where you can actually give that executor an allocator to, for example, allocate the stack size. So you can even control that. But the most interesting thing is you can have your user-defined properties. So you can have your priorities, you can have your stack size, you can have your name or whatever you want. And to use that actually is to use the require function. And you give the require function an existing executor and then all the properties you want. And this is a compile time thing. So you will get a compiler error if this executor cannot give you an executor that actually has this and cannot provide adapters that create, for example, the one-way function out of the two-way or whatever. Typically there are adapters, but if you don't have such, you will get a compile time error. So how does that work? Well, in your target implementation, you just implement your execution context. Well, that is essentially in my case, FreeRTOS, which is that create task function. And of course, on the host, you can do whatever you want. You can use the thread, you can use pthread or whatever is available, and you can, it depends on how much you want to model your reality. And the point is your application, well, that actually uses a prototype executor, because from that executor you can use the require function to get other executors with different properties. So you have your global prototype executor that is differently defined typically for the target or for the host, and then you can use just that one and use require to get new executors out of that with those properties that you actually need. And running out of time, I only will very briefly show you, so here's actually an example to just how to use the require. What's more interesting is here I have, not for the target, but actually for my Linux system, I have a real-time executor, which actually has a priority, and then if you actually need to get one, so here I have my implementation of the require, and for this require, and in this case I don't say I want a specific priority, I say for this specific function I want an executor with a priority of 80, so with a real-time priority. And then my mechanism, which is just concurrent data abstraction, that does the require on the function it is given, and that will tell it, okay, take one with a high priority. So that was it about executors. And now something that is a little bit less abstract, and we actually have a pretty good API for that one now, is the queues. And there are actually log-free implementations for that one for single-ended size. So this can be used between different tasks or between interrupt service routine or a task. So that they have a fixed size, and essentially you have a push, pop, and close interface. You can have wrappers where you only get one end of the queue, which is useful. And the stream iterator is just for debugging. Here's more or less the interface. So you have a mechanism to close it. You have a pop and you have a push. That is the main interface, but you have actually much more interfaces. So you have also a try pop or a non-blocking pop. So if nothing is available, it will still, the point with non-blocking is if you implement that with a mutex and you cannot grab the mutex, then it will not block on that mutex. So there's actually a pretty sophisticated interface. And that is a very old proposal, but unfortunately it's still not in C++20. And that actually will be in C++20, so it's much newer, which is a semaphore. So mutexes are in C++ not intended to signal between different threads or different tasks. So it's actually only allowed to unlock a mutex in the same thread where you locked it. And semaphore is a more general thing anyway, so you can use that one. So the interface is essentially acquire, release, and try acquire. And you can, counting semaphore, you can not only have one single thing, but you can have as many as you want. So you can give that number in the constructor. And you can say, it's a template about the minimum size that you want, and so there might be different implementations. And then mutex is just a special case of a semaphore, and in C++11, where we actually have a mutex, well, we decided to have the mutex more or less as a concept, and then we actually provided some mutexes, but it was deliberately decided that you can provide your own mutex types. And that is necessary if you have your own scheduler, for example. So it might be that in the future the mutex will actually be templated on the executor. And now, unfortunately, just a very brief outlook. So this is ARM Mbed. So essentially, what you have is you have your basic operating system. Well, that is more or less the same as you have on FreeRTOS. But then you have also a file system. Well, we have file system in the standard since C++17. So that is fine. And the other thing that you have is the event-based thing and the connectivity. And this is covered by ASIO, which is the networking library. It's called networking library for C++, because it has socket interfaces. But what it really is it's a mechanism to program event-based systems. And it's essentially a subset of Boost ASIO. So if you actually want to use it, I would recommend Boost ASIO if it's available for your platform. And unfortunately, it's only available for not embedded platforms, but it's not actually that hard to implement that on something like FreeRTOS. It's just, yeah, probably 4 weeks of work to have something, to have it bug-free and well-tested and so on, of course takes some more time, but just to have something can be done pretty fast. What's not part of it is security. And that was deliberately put out because the C++ standard is, well, not very agile. But security ciphers and so on, they are agile. So those crypto algorithms that you used 10 years ago don't make much sense anymore. So we decided, okay, we will not standardize this part. But this is also covered by the networking library. Okay, and this is really, that is also in C++20, because no, only stackless coroutines are in C++20. And if you ask Nishanov, who actually proposed them, he says, well, coroutines are a mechanism to turn state machines into normal functions. And that's it. But that is exactly what you typically have in embedded systems. You often have state machines. And then it really depends on what developers you have. Some developers are really happy to work with state machines, but other developers aren't. So for normal programmers that come out of university, they typically have problems to find in the state machine the actual flow of control. So with coroutines, you can actually write it as a normal function, well, not as a normal function, but as a coroutine, and but the compiler will actually rewrite it to a state machine. So you don't have to do it, the compiler will do it for you. That's the idea of coroutines, and that's why it's in here. So that's it. Here are the references. The slides will be on my homepage probably by Tuesday evening. Maybe earlier, but I can't promise that. And all the other things, well, there are actually papers that have often pretty good examples and information how to use these things. So for example, we have an explicit executors design paper that explains how all this fits together. It doesn't have the wording. That is an extra paper. It only has design. Of course, that is now a little bit outdated because it was decided to have a completely different interface, but still it explains what that require means and the difference between execution context and executor and so on. And all those papers are on openstd.org in JTC1, SC22, WG21 docs papers. And then this one is in the 2018 subdirectory, networking TS as well. And queues and semaphores are from the last mailing, so they are in here. So, according to that, I don't have time for questions, but I will be around, so thank you.